Hi everyone, welcome back to 1.6. So chapter 1 in general is about solving equations. However, we do kind of change gears for the last two sections and start to solve inequalities. So the whole chapter is technically solving equations and inequalities, except the first five sections has been solving equations. So we could solve inequalities now. And the only thing is that we have a slightly different way of referencing our answer, but the way we solve inequalities is almost identical to how we solve equations. So here in 1.6, we're just going to start solving inequalities. And then when we get to 1.7, it's just a little bit different. We just introduce some new properties that revolve around absolute value. But for now, let's talk about inequalities. So inequalities in general are expressions that describe the relationship between any two numbers. But what we're going to do here is have an expression that describes the relationship between a variable and some number. So previously we had x equals a finite set of disjoint numbers, right? Like the very last example in 1.5 said our answer was 2, 1 plus square root of 3, and 1 minus square root of 3, something like that. Three values that are all very different. And even if we didn't get weird answers like -3, 0, and 2, they're still disjoint. However, what we're going to have for inequalities is a solution set. And a set is just a set of values that make the inequality true. Now, you can say that equations also have a solution set. Only difference is now our solution set is going to be this nice, smoother set of continuous values. So it's a lot easier to satisfy an inequality than an equation. In an equation, we are forcing things to be equal to each other. But now in inequalities, we're just saying, well, one side can be bigger or one side can be greater than or equal to. So we have a little bit more leniency when it comes to that. It just means we're going to need to write our answer in such a way. So we also have three different types of inequalities that are all very, very similar to equations that we had in 1.1. In 1.1, we had conditional equations, inconsistent equations, and identities. And the same thing is true here for inequalities. An inconsistent inequality is just any inequality that is never true. An identity inequality is just any inequality that is always true. And conditional inequality is just any inequality that has one particular set of answers. So we use all of these words for equations. We can talk about them in terms of inequalities, but again, not really worried about you naming them, more interested in you being able to actually do something with them. So solving inequalities, like I said, is a lot like solving equations, except we have one added rule, only one. That added rule, aside from, writing our answer different, the rule itself, the only difference is that when we are multiplying or dividing by negative numbers, we need to flip the sign of our inequality. So let's talk about that. If you are doing anything in your inequality, it is functioning exactly like solving equations. However, in the very specific scenario that you have to multiply or divide by a negative number, you have to flip the inequality sign. Less than would become greater than would become less than, and so on for the greater than or equal to, less than or equal to. That's the only added rule when it comes to inequalities. So let's just get into doing examples. 2x plus 5 is greater than 3. And again, we solve these exactly like we solved equations. If this was an equation, you would subtract 5 on both sides. You would divide both sides by 2. But again, we got to be very careful when we're multiplying and dividing numbers. In this specific case, we are dividing by positive 2. When we divide by positive 2, we do not change the sign. Okay, well, -2 divided by 2 is just -1. Now, again, only added step, not an added rule, the added step to solving inequalities is that we need to write this as an interval. So we have been doing that all the way since P1. So x is greater than -1 says -1 and everything bigger than it. Specifically for just greater than, we're going to use parentheses. Don't forget that if it was greater than or equal to, we would use a bracket. So, and also parentheses for infinity and negative infinity. Infinity will never have a bracket. Negative infinity will never have a bracket. So just keep an eye out for stuff like that. And again, if you need inequality help, go back and check out the P1 presentation. Okay, 8 minus 3x is greater than or equal to 2. Again, if this was an equation, you would start by subtracting 8 on both sides, and then you would divide by -3. Except, however, we have the added rule that if we are dividing by -3, we have to flip the sign from greater than or equal to less than or equal to. And then from here, okay, -6 divided by -3 is +2. X is less than or equal to 2 says everything to the left of 2. And 2 included because of the less than or equal to. So -infinity up to 2. Okay, let's keep going. 7x minus 11 greater than or equal to 2 times x minus 3. If it was an equation, you would distribute 2. You would subtract 2x on both sides. You would add 11 to both sides. You would divide both sides by +5. And if we are dividing or multiplying by positive numbers, nothing changes. It only changes for negative numbers. So we get x is greater than or equal to 1. X is greater than or equal to 1 says everything bigger than 1 with 1 included. So from 1 to infinity. Okay. 7 minus 2x is less than -3. All right. Again, if it was an equation, you would start by subtracting 7. You would then divide by -2. But again, that's the key here. We're dividing by -2. So if we divide by -2, we have to flip the sign. Less than becomes greater than. And -10 divided by -2 is +5. X is greater than 5 says 5 and everything bigger than it. Okay, and parentheses for 5 since we have strictly greater than. Okay, 7 times x plus 2 minus 20 minus 4x is less than 3x minus 1. Okay, let's distribute 7 here. Let's distribute 3 here. And let's combine like terms. 7x minus 4x is going to be 3x. 14 minus 20 is going to be -6. And maybe if you have the foresight from 1.1, you already start to notice something is wrong. Well, let's combine our x's. So let's subtract 3x on both sides. Well, when we do that, it happens to go away and we're left with just -6 is less than -3. Okay, this is kind of weird. When we were dealing with equations, don't forget that when we were dealing with equations, if we got to a point that the statement was always true, 0 equals 0, 2 equals 2. When we got to a statement that was always true, that was the definition of an identity. And likewise, if we got to a statement that was never true, we called that an inconsistent equation. And same thing is true here for inequalities, except don't forget, we look at inequalities a little different from equations. So yes, if we had -6 equals -3 equals, like in equations in 1.1, we would say that was not true. But don't forget, this is an inequality. We need to determine if the inequality is true. Now, the question we ask, is -6 less than -3? Is -6 to the left of -3? And that is always true. So yes, maybe the values don't equal each other, but we're not looking for equals. We're looking for less than. And this inequality is true. If the inequality is always true, we say the solution set is all real numbers, -infinity to infinity. No matter what we plug in for x, this inequality will always hold true. Okay, well, you could probably guess what the next one's going to be. So here, let's distribute 2. Let's distribute 5. Let's combine like terms. 2x plus 3x. 2 apples plus 3 apples is 5 apples. -5 plus 3, you're $5 in debt, and I give you 3. You are now only $2 in debt. Well, let's subtract 5x on both sides, and that goes away on both sides, and we get 10 is less than -2. So again, it's not a matter of if these values are equal. We saw that in the last case, those values weren't equal, but we're looking for, satisfying an inequality, not satisfying an equation. And now I ask, is 10 less than -2? Is this inequality true? Well, 10 is definitely never less than -2. That's never true. So there is no solution. We would call this inconsistent. We would call the last one an identity, but it's more interesting for us to say what the solution set is. For inconsistent, more interesting for us to say no solution. Okay, so solving inequalities, I don't think all that crazy. Well, we're going to introduce another type of inequality called compound inequalities, where all it is we have multiple inequalities going on at the same time. Now, that's actually an interesting question, because if we have multiple inequalities at one time, are we looking to satisfy both? Are we looking to satisfy one or the other? And that brings us to this really interesting logic question. So this is a question you would you would study in the study of logic, logical mathematics. So it's the difference between and or. And there's a very big difference when we're talking about English and mathematics and likewise for or. So here's what I mean by that. If we're talking about English, if we're speaking, to each other, not in a mathematical sense, of course, because most people don't do that. But so let's say I'm going to my friend's house Friday and Saturday. What does that mean to you? That means that I'm going to my friend's house on Friday as well as Saturday. I am going both days. However, if I say I'm going to my friend's house Friday or Saturday, what we think is that I would go to my friend's house Friday or I will go Saturday, but I won't do both. And that's different from mathematics or. And yes, that's different from mathematics or. So English and says both need to be true. English or says that only one of them should be true. But mathematics and an or works like this. Well, mathematics and functions the exact same way. If we're saying two things and, both of them need to be true for it to be a true statement. However, mathematics or doesn't say one or the other, one either or. Mathematics or says at least one of those things need to be true. So if we're thinking mathematical or to my original statement, I am going to my friend's house Friday or Saturday. Now, mathematical or would be satisfied if I am going Friday, if I'm going Saturday, or I'm going both. So mathematics or is also satisfied in the case that it is and. So if I go at least one of those 2 days, I could go Friday, I could go Saturday, or I could go both days. We say go both days is and, but mathematical or says one or the other or both, and that would satisfy. So that's kind of complicated, right? This isn't the study of logic. This is the study of college algebra. So what we eventually bring this to is that or will be a union of intervals, right? If we're looking at two separate inequalities, we solve two separate inequalities. If we're throwing an or in between them, all we're doing is taking the union of those things, having one, having the other, union together, whereas and will be an intersection. So that's where it comes down to, but it's a good example to talk through. Let's get right into compound inequalities. So let's say we have 2x plus 7 is less than or equal to 1, or 3x minus 2 is less than 4 times x minus 1. So here's what I mean. What we do is we're looking for a set that if we plug in a value to both inequalities, at least one of them is true. So let's say, you know what, let's do the example first. So if we're doing or, we still solve each one separately. We're still going to distribute 4. We're still going to combine x's. We're still going to subtract numbers. And we're still going to divide by constants. So first one, we divide by 2. Second one, we divide by -1. But don't forget, when we divide by -1, we have to flip the sign. Okay, x is less than or equal to 3 says everything to the left of that should be a 3. Everything to the left of 3, and x is greater than 2 says everything to the right of 2. And now what or is telling us is that we are taking, oh, no, this should be the -3. My apologies. This should be the -3 right here. Okay. What mathematical or is telling us is that we want to take the union of these two things. So we just take those two intervals and put a union sign between them. Basically, that's basic. There are cases where it's actually a little simpler than that. We can, combine it into one, but everything to the left of -3 and everything to the right of 2 don't have anything in common. So here's what OR is saying. It's saying that we can choose any value in this solution set, and at least one of these two things is true. Maybe not necessarily both of them, but at least one of them is true. So for example, if we plug in -5, well, 2 times -5 is -10, -10 plus 7 is -3, and now -3 is less than or equal to 1. So this is satisfied. Okay, well, if we plug in -5 here, 3 times -5 is -15, -15 minus 2 is -17, okay? -5 minus 1, -6. 4 times -6 is -24. I think we said -17 on this side is less than -24. Well, that wouldn't be true, but that doesn't matter. Only one of them needs to be true. At least one of them needs to be true. So when we plug in -5, this statement's true, but even though this statement isn't true, the OR says one of them is true. We're good to go. Okay. And same thing, if you were to plug in 3, this one would be satisfied, this one would not. However, let's say we plug in 0, a value that isn't in the solution set. If you plug in 0, 2 times 0 is 0, 0 plus 7 is 7, and 7 not less than or equal to 1. So this one wouldn't be satisfied. Well, for us to satisfy this entire mathematical statement, that must mean that this one is satisfied. Let's see. 3 times 0 is 0. 0 minus 2 is -2. 0 minus 1 is -1. 4 times -1 is -4. So is -2 less than -4? No, neither of them were satisfied. But we knew that because 0 wasn't in our solution set to begin with. Okay, let's do another OR one. 3x minus 5 is greater than or equal to 7. 5 minus 2x is greater than or equal to 1. All right. Let's add a constant to both sides. Let's divide by 3 and -2. Don't forget that when we divide by -2, we have to flip that sign. And we get x is greater than or equal to 4. X is less than 2. Okay, well, those are the intervals. Everything bigger than 4, everything less than 2. And OR says take the union of them. And just make sure you write your answers in order. For example, 4 to infinity would be to the right of -infinity to 2. -infinity up to 2, and then 4 to infinity. Technically, you wouldn't necessarily be super wrong by writing just this, but for the case of what we're trying to talk about, or we want to make sure we're taking the union of these things. Well, now let's do and. And at the very end is identical, except we take the intersection of them, everything they have in common. Okay, so we're still going to solve each inequality the same. Let's distribute 2. Let's distribute 3. Let's combine some constants. Let's add or subtract constants on both sides. And now you know that we need to divide by 2 and divide by -3. And don't forget, we divide by -3. We're going to flip that sign. All right, so this says everything to the left of 5. This says everything greater than -2. And now what we want is the intersection of these things. What do they have in common? Okay. I'm going to go to the whiteboard just for a moment just to show you what this one looks like. I'm not going to do it for the next one, but just so you have an idea. Okay, so just to give the brief example of what an intersection would look like for intervals, since we didn't really do it in chapter P, we had -infinity to 5, -2 to infinity. So if we were to draw these on a number line, first one would be everything to the left of 5. And the second one would be everything to the right of 2. So if we want to take the intersection of these two things, it would be everything they have in common. Well, let's draw some spots right here. And we see the only thing that these two both have in common is this section in the middle. Well, what's this section in the middle? -2 up to 5. Everything to the left of -2 isn't true because everything to the left of -2 is not between -2 and 5. And same thing we could say for here, does not count here. So the answer to this intersection would be -2 to 5. So I'm going to go back to the presentation. Okay, so we get our answer to be -2 to 5. So for the next one, I'm not going to go back to the whiteboard and draw it, but it's good practice for you if you want to practice drawing intersections. So what we're saying is that this is the solution set. -2 to 5 is the solution set. That means if it's in the solution set, it will satisfy both things. That's the definition of or. We need both of these to be satisfied for and. So let's say we take 0, which is in the solution set. 0 minus 3, -3. 2 times -3 is -6. -6 plus 5 is -1. And -1 is less than 9. That part is true. If we plug in 0, 1 minus 0 is 1. 3 times 1 is 3. 3 minus 2 is 1. 1 is less than or equal to 7. So a value in our solution set satisfied both. And that's the key to and versus or. And you have to satisfy both. Or you only need to satisfy one of them. You can satisfy both, but you only need to satisfy one of them. So it's a little less restrictive. Now, if we were to plug in a value that is not within our solution set, let's say we plug in 6. Well, 6 minus 3 is 3. 2 times 3 is 6. 6 plus 5 is 11. 11 less than 9 is not true. 11 is not less than 9. So this one fails. And by definition, for and, the whole thing fails. Even though when we plug in 6, 1 minus 6 is -5. 3 times -5 is -15. -15 minus 2 is -17. Well, this inequality would be true, but since it's not true in both, it doesn't count. So our solution set is the intersection of each individual part's final answer. Okay, let's do another and example. Again, you can draw it on your own, but let's do it. Here, let's distribute 2. Let's combine some constants. Let's add or subtract some constants. Let's divide by -2 and 2. Don't forget here, when we divide by -2, we got to flip the sign. This says everything bigger than -1 with -1 not included. This says everything less than 3, 3 included because of the less than or equal to. So now, what are all the numbers that are in common from -1 to infinity, -infinity to 3? You could practice drawing it on your own, but that would just be everything between -1 and 3. So for example, if you plug in 0, 3 minus 0 is 3, 2 times 3 is 6, 6 minus 3 is 3, 3 is less than 5, that one's true. 0 minus 5 is -5, 2 times -5 is -10, -10 plus 7 is -3, -3 is indeed less than or equal to 3. So everything in the solution set is true, everything outside of the solution set would not be true. Try something outside of this solution set to prove to yourself that at least one of them fails. So again, for or, we're looking for a union at the end because only one of the two statements needs to be true. But for and, we're looking for an intersection because both of the things need to be true. All right, we can also have compound inequalities that look like this. Now, we're going to look at inequalities that look like this again in the next section. So it's important that we solve it here. But actually, solving inequalities like this is actually really, really nice. So what it turns out is that this type of inequality is actually an and inequality in disguise. However, when it's written in this way, so much easier to solve. Okay, when we're doing equations, or when we learned to do equations, we said we needed to subtract 3 on both sides. But never in equations did we have 3 parts. It didn't make sense to have this part equal to this part equal to this part, right? If they're equal, everything's going to be equal. So for inequalities, it's a little different because notice in all the questions we've done so far, there have been bounds to where our answer starts and ends in a lot of these compound inequality cases. So long story short, when you're solving inequalities that look like this, if you do something to one part of the inequality, you need to do it to all of the parts of the inequality. So when you go to subtract 3 to get x by itself, you're not just subtracting the inside part and one of the two sides minus 3. You are subtracting everything by 3. Okay? You subtract 3 everywhere. And now when you go to divide by 2, you divide by 2 everywhere. So we get negative 4 less than x less than or equal to 3. Well, if you were to draw all the values between negative 4 and 3, that would just be the interval. Negative 4 not included because of the less than, but 3 included because of the less than or equal to. So way easier to get a solution set. So if you plugged in something between negative 4 and 3, you would get this entire inequality is true. Let's plug in 0. 2 times 0 is 0. 0 plus 3 is 3. Negative 5 less than 3. That's true. 3 less than or equal to 9. Also true. Okay, so these are actually pretty nice. Let's do another one. Maybe we see this negative 4x. That's going to be a problem. Let's see what happens. We want to subtract 2 to start, but make sure we subtract everything by 2. Okay, we're going to divide by negative 4, but make sure when you divide by negative 4, you divide everything by negative 4. But also, we know that when we're dividing by negative numbers, we need to flip the sign. Well, in this case, we're going to flip both signs. So this less than will become a greater than, this less than or equal to will become a greater than or equal to, and now we get this. This is kind of ugly though. 2 is to the left of negative 3. That's not what the inequality is saying, but it's written to the left of negative 3. Ugh, that's not good. Here's what we're going to do. To solve this problem, all we need to do is just read it backwards. And what I mean by that is literally negative 3, instead of reading this as greater than or equal to, if we're reading it backwards, this is then negative 3 is less than or equal to x, which is less than 2. That's all it means to read it backwards. Literally go piece by piece and just read it backwards. Well, now from here, saying negative 3 to 2, not so shabby. Again, if we were to plug in something outside of the solution set, we've seen so many times outside of the solution set works, inside the solution set works. Let's plug in something outside. Let's plug in 3. Negative 4 times 3 is negative 12. Negative 12 plus 10 is negative 10. Negative 6 less than negative 10. Oh, well, that's not true. So part of this fails. Negative 10 is less than 14, but it doesn't meet that first bound criteria. So something like that. So inequalities, a lot like equations. Compound inequalities, also a lot like equations. Whole thing is just kind of like its own weird rule. And there exists one more type of inequality that we can solve when it comes to like rational inequalities, right? Where just one side is a fraction. So not super common here in algebra, but something like this is actually going to be very popular when you go to solve increasing, decreasing, and for extrema and concavity, all very fancy words in Calc 1. So I'm going to do some examples here, but odds are you're not going to do a ton of them in your classes, no matter where you're watching this. But if you're watching this for Calc 1, you definitely want to listen up. If I ever decide to make Calc 1 videos, I'll do those separate. But yeah, for now, let's do test point method. So we want to use it for anything not linear. So for example, quadratic, rational, etc. The steps are as follows. Make sure one side is equal to 0. We have to make sure one side is equal to 0. We're going to simplify everything as much as possible. And we're going to set the numerator and denominator, if we have it, equal to 0. We want to find all the locations where the numerator is 0 and where the denominator is 0. We're going to put those values on a real number line, which create multiple subintervals. Okay. And we're going to test values in those subintervals by plugging them into the original equation or an equivalent simplified version that we find, right? Our final answer is all the subintervals that are true, and we're going to ignore all the ones that are not true. So the last thing we need to do is make sure that the endpoints are either included or not included, parentheses versus brackets. These are a lot of steps. Let's just do some examples. So I'm going to move to the whiteboard, and I will see you in just a moment. Okay, so here we are on the whiteboard. Let's do x squared plus 4x greater than or equal to 5x plus 6. Step one, we need to get 0 on one side. So let's start by subtracting 5x. 4x minus 5x is negative x. Let's then subtract 6. X squared minus x minus 6 greater than or equal to 0. This side we can factor as x minus 3, x plus 2. And now let's set each one equal to 0. So I know it says greater than or equal to 0, but we just want some reference points. So let's set x minus 3, x plus 2 equal to 0. We're going to set each part equal to 0. So x is 3, x is negative 2. And now what we're going to do is take these 2 points and put them on this subinterval. I like to put 0 there as a placeholder, but it is not one of our points. Well, notice we have an interval to the left of negative 2. We have an interval between negative 2 and 3, and we have an interval to the right of 3. So our 2 points created 1, 2, 3 subintervals. And now what we're going to do is plug in a value in each of those 3 subintervals. And what we want to determine is if our inequality is true. So let's plug in negative 3 for the first one. Well, negative 3 minus 3 times negative 3 plus 2. Well, negative 3 minus 3 is going to be negative. Negative 3 plus 2 is also going to be negative. And a negative times a negative is a positive, and positives are greater than 0. So our left interval is true. And notice that I didn't even really care what the values were. I only care about the sign. And that's the benefit to us being greater than or equal to 0, or having whatever with one side equal to 0. If one side's equal to 0, all we're trying to determine is if it is positive or negative. Positive numbers are greater than 0. Negative numbers are not. So you can find the actual value if you want, but it's easier to just determine signs. Okay, so we know the left one is true. Let's do the next one. Okay, let's plug in 0 for the middle interval. 0 minus 3, 0 plus 2. Well, 0 minus 3 is negative. 0 plus 2 is positive, but a negative times a positive is a negative number, which is not greater than or equal to 0. So our middle interval is not going to be true. Okay, last but not least, let's check a number to the right of 3. Let's plug in, let's say 4. 4 minus 3 times 4 plus 2. Well, 4 minus 3 is positive. 4 plus 2 is also positive. It is 6, but it's positive. Okay, and a positive times a positive is indeed a positive, and positives are greater than 0. So that is true. So then we know our answer is going to be negative infinity up to negative 2 with 3 to infinity. And now all we need to do is determine which of each of our 4 things, 1, 2, 3, 4, have brackets or parentheses. So to start, negative infinity and infinity always get parentheses. Now negative 2, what we need to do is plug in negative 2 into our inequality to see if it is true. If it is true, it is part of the answer. We put a bracket. If it is not true, we don't put a bracket. So if we plug in negative 2, well, what we get, negative 5 times 0, negative 5 times 0 is greater than or equal to 0. So negative 2 works. And then same thing for 3. 3 also works because if you plug in 3 to x minus 3, that is 0. 0 times anything is indeed greater than or equal to 0. So our answer would be negative infinity up to -2 with 3 to infinity. That's an interesting looking negative infinity, but I know you guys get the idea. Okay, let's do one more example, and then we'll call it a day for this section. Okay, so let's do x squared plus 2x minus 15 over x minus 1 is less than 0. Okay, first things first, we got to simplify everything as much as we can. Numerator, x plus 5, x minus 3 over x minus 1 is less than 0. Okay, so what we need to do now is, even though we have a denominator, we still want to set each and every part equal to 0. Well, we get x equals -5, x equals 3, x equals 1. And you might be wondering, why are we setting 1, x minus 1 equal to 0? Why is 1 part of that? We never want the denominator to be 0. And that is true. However, notice that in what we were doing before, if the denominator was negative or positive, it could completely change what happens in the numerator. So yes, we're never going to actually plug in 1. However, we just got to be a little bit careful. So we set everything equal to 0. All right, let's put all of those values on a number line. We have -5, 1, and 3. And again, I like just putting 0 there as a placeholder. Not one of our intervals, but it's good to put there. We have everything to the left of -5, everything between -5 and 1, everything between 1 and 3, and everything bigger than 3. So our now 3 values created 4 subintervals, and there's nothing wrong with that. Now we're going to plug in a value into each of these 4 subintervals and determine whether or not the inequality is true or false. So I'm going to rewrite the inequality over here. X plus 5, x minus 3 over x minus 1, less than 0. Let's plug in -6 for here. -6 plus 5, -6 minus 3 over -6 minus 1. -6 plus 5 is going to be negative. -6 minus 3 is going to be negative. -6 minus 1 is going to be negative. So we have a negative times a negative is a positive, divided by a negative. Whole thing is negative, and negatives are indeed less than 0. So again, don't care about what the value is. We only care about the signs. Well, all negative numbers are less than 0, so this one's going to be true. Okay, let's do the same thing for x equals 0. That's the wrong thing. Let's do the same thing for x equals 0 to test a value between -5 and 1, and we'll see what happens. 0 plus 5, 0 minus 3, 0 minus 1. 0 plus 5 is positive. 0 minus 3 is negative. 0 minus 1 is negative. Well, negative divided by a negative is going to be positive, or actually we should probably look at it this way. Positive times a negative is a negative, divided by a negative. Negative divided by a negative is a positive, but positives are not less than 0, right? We want less than 0, so this interval not going to be true. Okay, we're almost there. 2 more values. Let's plug in a value between 1 and 3. I think 2 is a great choice. 2 plus 5 times 2 minus 3 over 2 minus 1. 2 plus 5 is positive. 2 minus 3 is negative. 2 minus 1 is positive. Well, positive times a negative is a negative. Negative divided by a positive is negative. And negatives are indeed less than 0. So that interval is going to be true too. Again, it's not a matter of what the value is in between 1 and 3. It's a matter of, if we plug it in, is the inequality true? Okay, and we are almost there. Let's test one more. Let's plug in 4. So we plugged in 2 here. All right. Oh, I erased too much. All right. Well, x plus 5, x minus 3, x minus 1 less than 0. All right. If we plug in 4, 4 plus 5, 4 minus 3, 4 minus 1. Well, 4 plus 5 is positive. 4 minus 3 is positive. 4 minus 1 is positive. whole thing is positive, right? Positive times a positive is positive, divided by a positive is positive, but a positive numbers are not less than 0. So that answer is not true. Okay, that interval is not true, I should say. So our answer is all the correct spots here and here. Well, that would be negative infinity up to -5. And then we skip all the way from 1 to 3. Now, you might be wondering why I was so quick to use parentheses. Well, you can go in and check each one, but actually a really good giveaway is the less than sign up here. So if we have a less than or greater than sign, there's no chance that we can ever be equal to 0. So we are always going to use parentheses if this is greater than or less than. So even for the other one, if it was greater than or less than, you could jump to that right away. But if you don't like this, check each value to determine. You would see that if you plug in -5, the numerator is 0. Well, 0 is not less than 0, so that's not true. If you plugged in 1, well, the numerator is going to be 1 squared is 1, 2 times 1 is 2, 1 plus 2 is 3, 3 minus 15 is -12. But 1 minus 1 is 0, and then you'd have -12 over 0. So that wouldn't work. That would have to have a parentheses because we can't be equal to 1. 3, same argument as -5. Top would be 0, but 0 not less than 0. So with that said, that's the end of 1.6. We got one more section in 1.7. It's actually a pretty nice section. We like absolute values. They get a little twisty, but not really so hard to wrangle down. So I will see you in 1.7. Bye.
Hi everyone, thank you so much for watching. I hope this lecture helped and that you learned something. Just wanted to give the brief disclaimer that this lecture for this section is based on and adapted from the section in College Algebra and Trigonometry, the 4th edition by J.S. Ratty, Marcus McWaters, and Leswowska-Zerpek. So just wanted to give that disclaimer. I'm not affiliated with any of the authors. I'm not affiliated with Pearson, the publisher. This is entirely a presentation and lecture I created based on the book. So thank you so much for watching, and see you in the next section.